Section 8.2 is a brand new topic. So far, you've learned how to find the antiderivative for a power rule function using the chain rule with just a generalized power rule. Remember that whatever is being raised to the power, you must have the perfect derivative of that in your integrand before you can do the antiderivative or the integral. Undoing logarithms, this has to be a perfect derivative. In other words, you have a function in the denominator with no power on it and the perfect derivative of that function in the numerator, then you have a perfect derivative of the ln of that function. If you have a single e in your integrand, then the power must be set equal to u. You must have the perfect derivative of the exponent, and once you get this, do whatever adjustment needs to be done and you get the perfect derivative, then the antiderivative is just e to the u. Now, some of these problems look really messy, but the structure is very simple. The structure will be one of these things, and you've got to focus on the structure and not on the complicated chaos in the problem. Just for some more review, the integral of sine is negative cosine because the derivative of cosine is negative sine. So you need that minus adjustment in your integrand before you can get the antiderivative. Also, whatever you're taking the sine of, you have to have the perfect derivative of it before you can integrate. That's the same for all of these. These are all true substitution integrals where you set the argument of the cosine equal to u. You have to make sure that the du is perfect, nothing's missing. Then you can just write your answer because the derivative of sine is cosine times the derivative of the argument. And antiderivative, you're just going backwards. Secant square of u du is the perfect derivative of the tangent of u. Secant tangent is the derivative of secant. Cosecant squared, you're missing a minus sign, so you adjust. Also, got to make sure your du is perfect. Cosecant cotangent is the derivative of cosecant, but you need a minus sign. If you know the derivatives of your trig functions, then you will know all of these integrals. A few more quick reminders. Tangent can be written as sine over cosine. Make sure that you have the perfect du, and that gives you the function on the bottom with the derivative on the top. The only thing missing is a minus. Do the adjustment. This becomes a perfect logarithm derivative. So you can keep the minus on the outside and say that you have the ln of cosine, or you can take that minus 1 and make it a power. Cosine to the minus 1 is the secant. Don't forget your perfect du. The integral of secant, again, that adjustment there by multiplying by secant plus tangent over secant plus tangent creates a perfect logarithm derivative as long as you have the du. If you do these two problems for yourself a few times, you'll never forget. Cotangent is just cosine over sine. Again, the function's in the bottom, perfect derivative on the top. As long as you have that du there, you've got the ln of the bottom. Cosecant uses the same type of process adjustment here to create a perfect logarithmic derivative. You just need that minus sign. So you do the adjustment and you get the opposite of logarithm of the sum. And we showed in the 8.1 video how minus the ln of the sum is equal to plus the ln of the difference. What we're learning new in this section is to find the antiderivative of a product or quotient rule. So if you take the derivative of the product, you're going to have the derivative of one piece at a time. So if I keep the u and take the derivative of v, then I keep the v and I take the derivative of u, I get this. Now, let's solve for just one part. So we're going to subtract the v du from both sides of the equal sign, and that gives me u dv equals the derivative of the product minus the other piece of that derivative. Now if I integrate each of these pieces. Integrating both sides of the equal sign means I integrate each of these parts. Keep in mind parts. The integral of the derivative of u times v minus the integral of v du. But if I have the integral of the perfect derivative, then this becomes just plain old u times v. I want you to memorize this. uv minus the integral of v du. uv minus the integral of v du. uv minus the integral of v du. So what we're going to be doing is taking one portion of a product rule derivative. Notice that these two things are multiplied. We're going to take a u part and a dv part, and we're going to do what's called integration by parts. So let's talk about how we put this thing together. Notice that we have a perfect product here. We have u times dv. So what we're going to do is figure out one factor of our integrand to set equal to u, and the rest of the stuff in the problem will be dv. Notice that the integrand is that product. What is dv? dv is the derivative of some function v that was in our original problem. So we need the v. We are saying something equals u and something else equals dv. We have to find the v. The way we find v is we're going to take the integral of what we set dv equal to. Then, to get the du part of our integral, we have to take our original u and find its derivative. So we're going to take our original integrand, split it up into two pieces. We're going to say u equals something and dv equals something. We're going to take the derivative of u and the integral of dv, and then we're just going to plug stuff into this formula. So here you have the process laid out. You want to figure out which part of your integrand should be the u. And here's something to go by. L stands for logarithm. If you have a logarithm in your integrand, it must be the u. That's your first choice. If there's no logarithm, you look for an inverse trig function. That would be your second choice to set equal to u. If you don't have either of one of those, you're going to go for the algebraic term. That's just the polynomial part. Fourth choice is a trig function. Fifth and last choice, and almost never happens, you would set your exponential function equal to u. But you're never going to get here. You usually don't even get here unless it's a trig function times an exponential. Once you've picked your u, then you're going to find the derivative of that. You're going to find du. Remember, the rest of the problem, once you pick the u, everything else you've set equal to dv. You have to find the integral of dv so that you know what v is. Now you've got the u and the du, the dv and the v. You're going to plug it into the formula and simplify. You've got to do that step right there. Simplify before you integrate. You will find that the integral that you have left over in your formula is going to be much simpler than your original integral. Okay, so let's look at this problem. Notice that we have a product. It's a 3x times a trig function. So algebraic and trig. We're going to look first at this cosine function. You always try substitution first. So it would be cosine of u. So you see it's a 5, I got an x, there's too much, so I'm going to set this piece equal to the u for my integration by parts. The rest of the stuff in the problem is dv. Now I take the derivative of u, which is 3 dx. Don't forget the dx is important. Don't forget this dx, it's important because you have to integrate this to get v. Now notice this substitution stuff I did before. That means my du is 5 dx. Multiply by the 5, divide by 5, integrate, I get the derivative of sine as cosine, so I get sine of 5x with the 1/5 out front as my adjustment. Now I have all of the parts to plug in to my formula. And what was the formula? It was uv minus the integral of v du. So I'm just going to plug stuff in. Here's u, here's v, minus the integral of v, just copy it down, du. Now you've got to simplify this before you move on. So here we have a 3 over a 5, an x, and a sign. This is done. You're just going to copy it. Minus a 3 over 5, sine of 5x, and a dx. So again, I go up here and I use this substitution thing. U is 5x, du is 5. I need a 5 to make a perfect du, so I multiply by 5 and I divide by 5. This piece is ready to integrate now. So you copy the first part, you just copy, copy, copy over and over. He's done. Now this piece is 3 over 25. The integral of sine of u du is negative cosine. And you are done with this problem. The best thing that you can do to understand how this works is to start taking derivatives of all of your answers. Simplify the derivative, see that you get this back, because when you do this product rule derivative and then you do this derivative, one of the pieces of this will subtract away and you'll be left with the other piece. It's really cool, and taking the derivatives of your answers is highly recommended because it super enhances your understanding of what's going on. Another example problem, we have a product, 5x times e to the power. E to the power is always your last choice for u. So the 5x is your u, the rest of the problem is dv. You find the derivative of u, and you're going to integrate e to the minus 2x dx, which gives me e to the minus, why? Because we had to adjust by multiplying by minus 2 and minus 1/2. So we have u, v, we're going to get minus the integral of v, just copy it, and du. Simplify this, so this becomes minus 5x e to the power all over 2, and this becomes minus a negative 5/2, so plus 5/2 integral of e to the power. Notice that this integral right here is the same integral that you did here. That almost always happens. If there's any difference, it's a sine instead of a cosine or vice versa, or your power has changed on a substitution, but usually it's the exact same integral over again. So we integrate this and we get e to the power over the derivative of the power. Now I want to make it pretty. This is minus 5/4. The first part gets copied. Simplify the second. Notice that both of these terms has an e to the 2x. Both of them has a minus and a 5. And I'm going to get a common denominator and factor out, all the common factors. This got multiplied by 2 over 2. So this is a 2, and I wrote it down wrong. And you see how much more simple the factored answer is than just writing this down. So I multiplied this by 2 over 2, factored out the 5 and the minus, and the 4 in the bottom, and the e, and I got common factors of this, and this was what was left over. when you check your work, you're going to want to factor it and do a single product rule derivative. Instead of doing this product rule and then the derivative of this and simplifying, you can do it just one product rule here. New problem. Notice we have a logarithm. That is your first choice for you because you don't know the integral of the ln. You only know the derivative. So we set that equal to u. The rest of the stuff in the problem is your dv. Don't forget the dx. You'll see why he's important in the next problem. So the derivative of the ln is 1 over x dx. Integrate 3x squared and you get x cubed. So we're copying down now u v minus the integral of v du. You've got to simplify this before you do anything else. We have an x cubed on top and an x on the bottom. This becomes plain old x squared. Notice that you integrated x squared up here. So this gets copied, just make it pretty. You're integrating plain old x squared dx. So copy, minus x cubed now over 3 plus c. And then you can factor out the x cubed, get a common denominator and factor that out. Leaves me with 3 ln's minus 1 plus c. Again, to check your work, take the derivative of the factored form of your answer. What if we had just plain old ln as our integrand with nothing else? We still have to set the ln equal to u. But what's left in the problem to be the dv? Well, the only thing left is dx. So we set u equal to the ln and dv equal to the dx. What are you going to get when you integrate this? We know the derivative of the ln is 1 over x dx, but when we integrate a dv, we get a v. When we integrate a dx, we get an x. So plug it in, copy the u times the v minus the integral of v du. And remember, you have to simplify. So when we simplify this part, the x's cancel, and we just get the integral of dx again, just like we did right here. So copy the x ln x, minus the integral of dx is in minus another x, and you see we can factor out an x and make that pretty. By the way, ln of x can never be separated. This is not ln times x. This is one piece. It's a function all to itself. The x value is inside the logarithmic function. This is not multiplication. Do not ever write ln without something to be the ln of. You can't separate this. All right, how many of us remember what arctan is the derivative of? I don't, so I'm going to have to derive it real quick. Once you derive it, the derivative of the arctan, you will never forget it, okay? So I'm going to, over here on the side, show you how to find the derivative of an inverse trig function. I think I'm going to end up needing more room than I have. Set y equal to arctan. I know this is u, but we're going to use y. So if y is the arctangent, then the tangent of y equals the x. Take the derivative of both sides of that equation. Derivative of x equals secant squared y times the derivative of y. All right? Now it's the derivative of y that we were solving for. So we're going to divide both sides by secant squared, but that's the same as multiplying by cosine squared. We have cosine squared of y times a dx. We can't have a combination of variables. So I'm going to figure out if y is my angle and x equals the tangent of that angle. Tangent is opposite over adjacent. Notice that this is x over 1. So if these are my sides, then my hypotenuse is the square root of the sum of the squares. Now the cosine of this angle will be adjacent over hypotenuse. Isn't that the coolest thing ever? I know, right? So if dy equals cosine squared, then I need to solve for cosine squared of y, which just squares this thing and gives me this. Now you see that dy, or in our case du, is going to be 1 over 1 plus x squared times dx. Isn't that the coolest thing ever? So you can always derive the derivatives of the inverse trig functions if you've forgotten them. So if u is the arctangent, then du is going to be 1 over 1 plus x squared dx. Plug it into my formula. I'm going to have u times v minus the integral of v du. Now, how are you going to integrate this part? Well, it's just a straight up substitution. Set the bottom equal to u. Find the derivative of that. It's 2x dx. Notice that I have an x here. All I need is the 2. So I multiply by 2 and I divide by 2. And now I'm ready to do this part of my integral. I copy the first part. I'm going to move this x up front. And then I have a 1/2 integral of du over u, which is a perfect logarithm derivative of 1 plus x squared plus c. Isn't that gorgeous? Okay, just to review, and it's the arcsine and the arctan that we always run into. So we developed the derivative of arctan. Let's do arcsine the same. So if y is the arcsine of u, then y is the angle and u is the value of sine. So the derivative is the cosine. Solve for dy, which means we're going to get secant y du. Y is the angle, and we're showing right here that the sine is u. That's u over 1. So u is the opposite, 1 is the hypotenuse. The other side will be subtraction. Hypotenuse squared minus that side squared. Now we need the secant of y. Well, the cosine of y is going to be the square root over 1. So the secant will be 1 over the square root du. And now we have the derivative of the arcsine of u. So 1 over the square root of 1 minus my function squared times the derivative of the function. This is very important that you remember. You will be using these things. So the integral of du over root 1 minus u squared, we can't do a substitution integral because if we set the blob equal to u, we would need the derivative of this, and we don't have the net missing piece. But remember these two integrals, they come up a lot. And there you go. This was 8.2. Do your best on the homework and contact me with any questions you have.